All right, very good. So welcome everybody to the last day of our conference/school. And our speaker today is Kyrylo Snizhko from Grenoble. And he's going to tell us about general theory of chiral state conversion in non-Hermitian systems. And in honor of the conference, he has dressed up.
Good morning. Good morning. I'm going to tell you today about the work together with Parvin and Yuval, so feel free to bother them with questions as well as me. Before I go to the essence of the talk about non-Hermitian state conversion, I'd like to say that I've been here before. 4 years ago, I was here at the same institute and gave a talk in a quarter. I got 2 quarters back then, so you know I'm finishing the cycle. You know, I come from Ukraine, and we have some sort of a traditional cloth over there too, which looks not too dissimilar and actually looks nice in the Indian context, if you ask me. Speaking of Ukraine, you know, I'm used to thinking of Ukraine like this. But some time ago, I needed a logo that involved the Ukrainian borders. So I asked a Frenchman to draw me a logo. I don't remember the details of the logo, but the borders of Ukraine looked like this. And I did not quite understand why. What is he trying to say by, you know, tilting my country? And then I understood the reason. I went to the French Wikipedia page about Ukraine and saw this map. Of course, if France is the center of your world, Ukraine does look like this. So that's actually the message of my talk today, that what you focus on largely determines what you will see. And if your focus is wrong, you may miss something important. For example, if you focus on Europe, it's very easy to miss India. But figurative speech aside, we are talking about non-Hermitian Hamiltonians today. What are these non-Hermitian Hamiltonians? You've studied quantum mechanics, so you all know the Schrödinger equation with Hermitian Hamiltonians. Turns out that even in the realm of quantum physics, you can get non-Hermitian Hamiltonians. Same Schrödinger equation, but the Hamiltonian is not Hermitian. For example, it can be like this. One of the levels decays. And what could be the reasons for such Hamiltonians? Well, you have levels or particles or quasi-particles with finite lifetime. Or you have measurement in your system and you post-select the measurement results. Or you can think of a Lindbladian system and use the third quantization formalism and map it to a non-Hermitian Hamiltonian problem. There are a bunch of reasons why non-Hermitian Hamiltonians could appear in quantum systems, but also in classical systems. For example, if you think of an optical system with losses or where you pump energy into some of the optical modes, that's naturally describable by a non-Hermitian Hamiltonian. Electric circuits with resistance, mechanical systems with friction, pretty much anything which is linear and has loss or gain is describable by a non-Hermitian Hamiltonian. If you want to know more about this physics, I thoroughly recommend this review article. Now, when people talk about non-Hermitian Hamiltonians, they often like to focus on their special property called exceptional points. What is an exceptional point? If you think of a Hermitian Hamiltonian, you are guaranteed to be able to diagonalize it. Diagonalize it via a unitary transformation, and D will be a diagonal matrix of eigenvalues. Some of the eigenvalues make inside, then you say there is degeneracy, but the matrix will always be diagonal. This is not the case for non-Hermitian Hamiltonians. You can try to diagonalize it, but first of all, the matrix will not be unitary. Most importantly, though, the matrix J in the middle is not guaranteed to be diagonal. It's guaranteed to be of Jordan form. Part of it is diagonal, and it can have this one of diagonal elements. There can be many of diagonal elements, but you can always make them to be equal to 1. The simplest example is the sigma plus operator. You cannot diagonalize it. There is no simpler form for it. So whenever you cannot diagonalize a non-Hermitian Hamiltonian, whenever you get these off-diagonal elements, that's called an exceptional point. You kind of get the degeneracy of eigenvalues, but there are not enough eigenvectors. The eigenvector corresponding to this will also generate the other vector contributing here. So there are not enough eigenvectors in this matrix. Whenever this happens, that's called an exceptional point. You can ask, what use can we find for non-Hermitian Hamiltonians? Well, people found quite a few. For example, you can use some ancillaries, do some post-selection, and improve the behavior of quantum optimization algorithms. Or if you consider qubits that can decay out of the computational space, you can entangle them much faster than with the similar coupling Hermitian Hamiltonians. And if you operate a detector close to an exceptional point, you can enhance its sensitivity under some conditions. You can also have some interesting devices. We'll talk about this device a bit later. I want to give you a warning, though. Whenever you hear about usefulness of non-Hermitian Hamiltonians, you need to have some caution. Because here, for example, you can entangle qubits much faster if they remain in the computational space, but there is some probability to decay outside of the computational space. And when they do, you don't even have a qubit, not to talk about entanglement. So you have to be careful what exactly non-Hermitian Hamiltonians can give you. But I'm doing here fundamental science, so I'm not interested in usefulness today. I'm interested in how things work. And I want to focus on the effect of chiral state conversion. What is chiral state conversion? You have the Schrödinger equation here, and the Hamiltonian changes in time. And let's say it changes over time capital T. And let's say capital T is a long time. It changes slowly, something that from Hermitian systems we would call adiabatic limit. People have studied that problem, have studied it, as far as I know, since 2011. And they found some interesting properties. You can start with any state. For example, they start here with state up populated, and here they stay down populated, and you look at the evolution, and the state quickly decays to some eigenstate of the Hamiltonian, and then it follows it. Moreover, if the Hamiltonian trajectory goes around an exceptional point, the Hamiltonian is always diagonalizable on this trajectory, but it goes around an exceptional point. Then you can get this state conversion to be chiral. If you trace the loop in one direction, you convert any initial state to one eigenstate of the Hamiltonian. If you trace it in the opposite direction, you convert any state to the other eigenstate of the Hamiltonian, to another eigenstate of the Hamiltonian. That's called chiral state conversion. And exceptional points that the rate of change in your Hamiltonian is much smaller than the distance between eigenvalues. They are complex, absolute value difference. Absolute value difference is what matters. Not absolute value difference. Difference and the absolute value of this difference is what matters.
Sorry, Kyrylo, to follow up on that, you had a Hermitian Hamiltonian, the rate of transition would be zero.
Yes. And yes, and the rate of transitions is still zero because you see it follows the eigenstate, but before that, it decays to one of the eigenstates somehow. And we'll talk about why it decays and how this conversion kind of non-adiabaticity, apparent non-adiabaticity happens. We'll get to that in a couple of minutes. But when we talk about chiral, people believe it's related to exceptional points. For example, in this work from 2017, people considered this Hamiltonian. These are the eigenvalues, eigenstates, and at some special values of the parameters, the eigenvalues coincide. and you can check that they become zero. So the two eigenstates collapse on top of each other. And therefore, there is only one eigenstate for a 2x2 Hamiltonian. That's an exceptional point. And if you look at the eigenvalues, you go around the exceptional point, and there is a branch cut because of the square root. So you go around, and the eigenstates flip, they change their roles, and that's believed to be the reason for the chirality of this conversion. So these were theory works, and this behavior has been observed. Here is a Nature from 2016, infrared radiation in waveguides. They observed this chiral state conversion. This is the device I mentioned before, and I like this paper because it has a beautiful picture. You inject some light from the left. It's polarized vertically or horizontally. Whatever exits on the right may be dampened, but it's always horizontally polarized. And if you inject it from the right, whatever you inject, the light exiting on the left is vertically polarized. So you see, it depends on the direction the light propagates, and you convert anything to a specific state depending on the direction of propagation. And this has been observed on actually many platforms, also in electric circuits and in proper qubits. This one is with NV center qubit. So this has been observed. Well, I can stop the talk and we can all go home or wait for the next speaker. But if you examine the literature carefully, what turns out is that there are exceptions. There is theory and experiment that you can go around an exceptional point and not get chiral conversion. You still get conversion, but it's not chiral. Or there is another theory paper saying that you can get chiral conversion without going around an exceptional point. And last year, there was a Nature where the experiment confirmed this, that this can happen. People are surprised, people are interested, and people do not really understand what happens. Well, that's why I'm here today. I'm going to tell you how this happens and what's the physics of this system. Before we understand the exceptions, we'd better think of non-Hermitian adiabatic evolution, what people studied before, multiple theorists using different methods, typically about two-level systems. I will present you the same theory in the way I like it, which is applicable to Hamiltonians of any size. So how does non-Hermitian adiabatic evolution work? You have the Schrödinger equation, and the Hamiltonian evolves over time capital T. Typically, people think of a closed evolution. The Hamiltonian in the end is the same as in the beginning. I will not require that. Any Hamiltonian trajectory is fine for me. But what I will require is that on the evolution trajectory, there are no exceptional points and no degeneracies, so that I can always diagonalize my Hamiltonian. And the eigenvalues are always distinct, so that if I go sufficiently slow, the difference between the eigenvalues can be made larger than the rate of changing the Hamiltonian. And these unitary, these not unitary, but some transformation matrices, they encode the eigenbases of this Hamiltonian. So I can define instantaneous eigenbases at each point in time. I can decompose my system state over this instantaneous eigenbasis with some coefficients that will evolve in time. Had my Hamiltonian not changed, I would have an easy time solving this equation because the coefficients would then look like this, the same as Hermitian system, except for the lambda is complex. So the real part gives you phase oscillations, but the imaginary part allows you to have growth or decay of these coefficients. So non-Hermitian Hamiltonians, they do not preserve the norm. You have to keep that in mind. These complex parts allow for growth of coefficients. No, that's basically the issue of non-Hermitian. For Hermitian, eigenstates should be orthogonal, Non-Hermitian, no, and that's why when you approach an exceptional point, several states can coincide. Right, right. Correct. There is an orthogonality condition that if you act on the right and if you act on the left, the eigenstates will be different. There are left and right eigenstates, and left and right eigenstates are mutually orthogonal, but because right eigenstates do not have to be mutually orthogonal to each other, this collapse can happen, the exceptional points can. Right. So if the Hamiltonian had not evolved, this would be the dynamics of my coefficients. Some coefficients grow, some decay. And if I sit and wait for a sufficiently long time, the state would align in itself with the most growing state. You had a question.
How do you take care of that statement, no exceptional points or degeneracies?
I say, if you give me a trajectory, and I can check that on the trajectory there are no exceptional points, then what I'm saying will be correct. If you give me a trajectory through an exceptional points, I'm going to have a problem. My theory is not going to apply. So there are imaginary parts, they determine growth. And if you just sit and wait and the Hamiltonian does not change, you will get converted to the most growing state. You will get aligned with the most growing state. I'd like to call that sit and wait conversion, although that's not an official term. But our Hamiltonian, it changes in time. So the picture is a bit more complicated. How does it work? Let's switch to the basis of instantaneous eigenstates. Then the Schrödinger equation becomes simpler. We have the diagonal matrix, but we also have a correction, a small correction because the eigenbasis changes. This correction is small, it's 1 over capital T, but it turns out to be crucial, so you cannot neglect it. Therefore, what you have to do is you take, you diagonalize this matrix, switch the basis once more, and the correction, you get a new corrected diagonal matrix, and the correction due to the change in basis becomes smaller. Here you can neglect it, or you can continue doing this basis switchings to make this correction arbitrarily small as you wish. Eventually you get the answer. What's the answer? The answer, we're interested in the evolution operator of the system. So time-ordered exponential of the Hamiltonian. And in the adiabatic limit, when capital T is sufficiently large, you can solve for this operator and you represent it like this. This is just switching to the instantaneous eigenbasis of your Hamiltonian. This is the exponential growth. Just now, it takes into account that eigenvalues change in time, and you expect conversion to a state with the biggest integral of the eigenvalue. So sometimes it can grow, sometimes it can decay, but the most growing state overall is supposed to win. And now these things that come from that correction I mentioned are weak shaking. You go slower, the shaking will become smaller. What's the role of that? Well, imagine I start in some eigenstate, which is not the most growing eigenstate overall. I would say adiabatic evolution, I stay in that eigenstate. But because of this shaking at the beginning, I will generate populations, small populations, 1 over capital T populations in all of the instantaneous eigenstates. And the most growing state will eventually overtake everyone else because, okay, the population is 1 over capital T, but the growth is exponential. So that's actually what ensures you non-Hermitian conversion. And coming back to the notion of chiral state conversion, what people believe, yeah. A question.
In the previous slide, so this condition of weak shaking, is it inside the Hamiltonian?
Which condition we're checking?
Weak shaking, the WT.
Weak shaking.
Yeah.
It's here. It's this operator. What
yeah.
do you want to know about it?
I mean that statement comes from the previous statement, right? The time ordered of
yes,
the exponential.
It's an exact expression for this thing.
Okay, so this information is in the Hamiltonian.
This information is in the Hamiltonian change in time. This weak shaking comes from this correction.
Okay, okay.
Because I start my evolution and my
Yeah.
basis changes,
Yeah.
but as my basis changes, the evolution is not completely adiabatic. There are corrections 1 over capital T,
Okay.
and these are exactly that correction. So Hamiltonian knows about it, but it comes because the Hamiltonian evolves in time.
Okay, okay. Understood.
Absolutely, absolutely. The only thing is the interpretation. For a generic non-Hermitian Hamiltonian, I can say I will have growth and some of the states will be most growing. For Hermitian, I won't have growth. So all this will do is just some phases. Any other questions?
What's the notion of gauging variance between input and
Oof.
because without that, there is no well-defined notion of
Good question. Let me say that geometric phase, it's exactly the correction between delta 1 and D. That's the difference. And well, it's geometric because it does not depend on capital T. And if you have a closed trajectory, then the gauge invariance is automatic. Absolutely the same as in the Hermitian case. Just everything. Well, if I don't have degeneracies, all I can do is multiply this vector with some number. Okay, and the gauge transformations will be about the phase. Okay. Let's talk about this after the talk, because I'm not talking about geometric phase. They are completely irrelevant here. There was a question over there.
What was the question? Sorry, maybe next time you can use
the question was about geometric phases, and maybe we'll get back to this issue after the talk. So basically, that's the theory. You get converted to the state which has the biggest integral of the imaginary part of the eigenpath. And the wisdom about chiral state conversion is that you take non-Hermitian Hamiltonians, which have sit and wait conversion, have adiabatic dynamics. So even in the Hermitian case, you would follow the eigenstates of the Hamiltonian, the instantaneous eigenstates. But together with sit and wait conversion, this is non-Hermitian conversion. You get converted to the most growing eigenstate, and then you follow it. Now, what people say is if you combine that with an exceptional point, you get chiral state conversion. Let's examine the validity of this theory I've presented to you. We have non-Hermitian Hamiltonian. You've seen I can decompose the state over plus and minus eigenstates. I'm going to take the normalization constant outside of the brackets because I'm not interested in the overall normalization. I'm interested in the direction of the state. And this allows me to look into coefficients C plus and C minus normalized because the normalization constant I took it out. So we take the Hamiltonian, we follow some trajectory which is open. What do we see? There are states. Here is the dynamics of their eigenvalues. For example, the plus state, it initially decays, but then it grows because the imaginary part becomes positive. If you look at the integral, overall, it grows while the minus state decays. So that's what the theory would predict you. Even if you start from the minus state, eventually the minus state will become negligible and you will get all the weight in the plus state. And the numerics tells you exactly the same thing. So the most growing state wins. The theory is correct qualitatively. Quantitatively, see the point of this jump, it does not exactly align between theory and numerics. You may dismiss it as a minor detail, but if you follow the same trajectory in the opposite direction, now the plus state still grows the most. It grows while the minus state decays. And in the beginning of the trajectory, yes, the minus gets down converted, you get all the weight in plus, and the theory says you would stay there. But numerics, the way to fix it is to, yeah, I think I'll be on time. The way to fix it is to introduce noise. Why so? Because our system features exponential instabilities. And therefore, a small change, a small noise can have drastic effects. That has to be taken into account. So on top of our slowly evolving Hamiltonian, let's add some fast noise, small noise, but something that cannot be incorporated into the adiabatic approximation. Then the new evolution operator, taking noise into account, I can use perturbation theory and say it's the old evolution operator plus a small correction because of noise. What's the nature of this correction? The correction introduces weak shaking in the middle of the trajectory. I evolve for some time, I get converted to the most growing state, and then I shake, and I repopulate all instantaneous eigenstates. And then the conversion process starts again. And this happens because there is an exponential instability in my system. So I get shaking, which can happen towards the end of the trajectory up until the very end. So the state that will win in the presence of noise is not the most growing state over the whole trajectory. It's the state that grows the last. Before we analyze numerics, what can be the sources of noise? The sources of noise can be noise and control parameters that happens in an experiment. Or you can have undesired perturbations in your system. So experiment will definitely have uncontrolled noise. What about numerics? Well, we do time discretization. So we will have trotterization errors, and they can be interpreted as noise as well. So numerics will have errors. Experiment will have errors. The old naive adiabatic non-Hermitian theory did not have noise. But once we put noise in, we should be okay. We should reconcile all the discrepancies. So let's compare. This was our problematic example. With the conversion, numerics did not, numerics predicted, the adiabatic theory did not. What do we see? At the end of the trajectory, the minus state grows, the plus state decays. So the state that wins, it's ultimately the minus state according to the numerics and according to the theory that incorporates noise. We've restored qualitative agreement. Now, in fact, this theory allows you to have quantitative agreement. Of course, for that, you need to put noise by hand so that you know what's happening. But we do that, a very tiny noise, 10 to minus 4. And what do we see? We get a perfect match with numerics qualitatively, but also quantitatively. And we went over the known examples from the literature, and our theory allows to explain these examples too. So exceptional points and chiral state conversion, is there any relation? I have an open trajectory here. I don't even go around an exceptional point. I go in one direction, I get converted to the plus state. I go in the other direction, I get converted to the minus state. It's chiral, it's direction dependent. No exceptional point is relevant in the game. So exceptional points were the focus, and people missed what was actually important in the system, which is noise and the structure of eigenvalues. So this naturally brings me to my conclusions. Ukraine looks like this. You should never forget about India. And if you happen to deal with a system featuring instabilities, you'd better take noise into account. By the way, small detail, for the slow non-Hermitian evolution, we now have the theory, not a theory, but the theory. Thank you.
Let's make some noise to show our appreciation. And some more noise.
Just a comment about the geometric phase in the case of non-Hermitian conditions. So when you have a system subject to a dissipation or non-hermiticity, you can define a geometric phase which will have a real part, which is the conventional, call it a geometric phase or Berry phase, which is modified by the presence of the environment. And then you have an imaginary part. And this imaginary part is called the geometric dephasing. It dephases the system. It can be both positive or negative, so it can resurrect the state. But it has all the properties of being geometric, namely only after you complete a closed circuit, you will see this effect.
Yeah, so before that, I just want to make a comment as to what Yuval said. Yuval, I understand what you're saying, but we need to define it in a proper way. We need a notion of gauge invariance. And I think the notion of gauge invariance for non-Hermitian Hamiltonian seems to be a little problematic, because you will have to have a gauge transformation which is e to the power I theta, where theta is not just a phase. And then you can define a generalized notion of gauge invariance. From there, if you arrive at this expression, then you can say it's geometric in the proper sense. So that was my comment. So now let me move ahead. Now what was? So I think if you go back to the discrepancy, at least the exceptional point discrepancy, I don't think any noise you don't need any noise to explain that, because it's just saying that you're on a Mobius strip. So to explain more, basically, if you go twice around the exceptional point, you come back to the same state with a -1 phase. Now, if you do not do that, if you do one circle, you actually do not come back to the same state, but it depends on which way you go, and that can be reconciled as a non-abelian Berry phase. So if you don't come back, but you come back to the same point in the parameter space, and you can just reconcile it as a non-abelian phase. And if you go one way, you get one non-abelian phase. If you go the other way, you get another non-abelian phase. And that can be pretty much explained without any invoking of noise. So that's just a comment. I mean, rest, I think what you showed, open loop trajectories, I have to think.
Well, I think what you're making a comment about is not discrepancy, but just non-Hermitian conversion. And that can be explained without any noise, although I would hesitate to call it a non-abelian geometric phase or phase, for the simple reason, these two states here at any point in the parameter space, they are not degenerate. For example, here you look at the imaginary part of the eigenvalue, the two states clearly have a different. So it's not a degenerate subspace in which you have a geometric phase. It's really a dynamical phenomenon.
Yes, here. Sorry.
Go ahead.
Oh, yeah. Okay. So the type of non-Hermitian Hamiltonian that you just mentioned. So do we see any kind of like change or dynamical, behavior in the ground state eigenvalue and the ground state eigenstate?
Once more.
Do we see any kind of specific behavior of the ground state and the ground state eigenvalue for this kind of Hamiltonians?
Which kind of Hamiltonian?
Non-Hermitian.
Well, non-Hermitian Hamiltonian is a matrix. In principle, if you say, I want these eigenstates and these eigenvalues, you construct your non-Hermitian Hamiltonians. So if you ask some specific properties about ground states, you'd better specify what you're dealing with. And people do study, for example, many body non-Hermitian Hamiltonians. They see some interesting properties. For example, when it comes to topology in your system, there are unusual properties of topological non-Hermitian systems. There are unusual properties of eigenstates. For example, you can get bunching of eigenstates at one side of your system, which is called non-Hermitian skin effect. So yes, in principle, non-Hermitian Hamiltonians have new phenomenology. But as far as I'm concerned, whatever non-Hermitian matrix you give me, I'm telling you about its slow evolution and state conversion. Yeah, and one more thing, when you talk about non-Hermitian Hamiltonian, you have to be careful to define when you say ground state. Are you talking about the state that decays the slowest, or the state that has the lowest energy, the lowest real part of the eigenvalue? Because these need not be the same state. Lowest energy. Well, I'd say the value of lowest energy when you have non-hermiticity explicit becomes way smaller than in Hermitian Hamiltonians. In Hermitian Hamiltonians, you say everything decays to the lowest energy. Here, when the decay is incorporated explicitly, even if it's the lowest energy, it can decay to some other state.
Right. Let's thank Kyrylo again.